Yesterday in class, what we did was we took what we learned on Friday, which was you need to know the properties of these two graphs. Is there anybody who was not here Friday and was not here yesterday? Okay. So again, I'm posting videos of the lessons when there are a number of people absent. And again, despite everything that's going on in the world right now, we still have some responsibilities, right? So I would say your responsibility as a student is to watch those videos. They're posted, the links are posted, they're YouTube links, and they're posted in your Google Classroom. So anytime you're away, you should be going to Google Classroom and seeing if there's something there. And if you go into Google Classroom in the morning and there's nothing there and you're going to be away, check later on, because if I record a video, it may not be posted until late afternoon, early evening. And I'm doing that to help you out so you don't fall behind, because when you fall behind, the stress is just going to keep snowballing. So on Friday, we learned the properties of these two graphs. We talked about amplitude. The amplitude of each of these types of graphs is the distance from the middle of the graph vertically, which I'm going to mark with this dotted line, to either the maximum or the minimum. So this is the amplitude, or this is the amplitude. And we can do the same thing with sine of theta. But the bottom line is the amplitude of either of these graphs is 1. What's most significant is that these graphs repeat every 2 pi. We call that the period. And the start point for sine is, I want to say it's at the origin, but I want to make this more general for what we did yesterday. The start point for sine is on the midline of the graph. Okay? Because if we shift things around, the origin is not where it starts. It starts on the line that's the middle horizontal marker for the graph. And it goes up from there. So it starts in the middle and goes up. Cosine, on the other hand, starts at the top and goes down. What we learned is that if you were to multiply this function by a number, which we call a, that affects the amplitude. And if you were to multiply, in this case, theta by a number, which we call b, that affects the period. So the amplitude, which is capital A, is equal to the absolute value of lowercase a. The period, which we give the symbol of k to, the period can be found by taking 2 pi divided by whatever b is as an absolute value. And if you want to work in degrees, then you would go 360 divided by b. This that I've just talked about here, I'm just going to go a little bit slower here at the beginning because I want to make sure everybody's caught up as we can get them caught up. These two things that I have talked about, along with the pictures of those two graphs that I just showed you, are Friday. That's what we did on Friday. What we did yesterday is we said we can now shift these things horizontally, and you're probably accustomed to using the letter h for the horizontal parameter. Unfortunately, we don't use h with trigonometry, we use c. And we call that, instead of calling it just a horizontal displacement, we often call it a phase shift. Sorry, buddy. And the phase shift can be expressed with a negative. So if c is negative pi, then we can say the phase shift is negative pi. There's nothing wrong with that. I like saying the phase shift is pi to the left. I think that's more informative. It tells you something that negative pi doesn't tell you. And d is the vertical displacement. If you stop and think about this, and I'm going to use an example to illustrate this. If we take a look now at your homework assignment or the practice problems that you were given, and I'm just going to pick on F, 1F, just because. Forget about the fact that there is a horizontal displacement here, or a phase shift. There is a phase shift of pi over 4 units to the right. Forget about the fact that there's a b value of 1/2, which is going to change the period. I don't care about that right now. What I want everybody to focus on are the values of A and D, because I want to have a discussion about range and max and min. So when we have sine of theta, and I'm not going to worry everybody about drawing multiple periods. I'm just going to draw from 0 to the end of the period. When we have y equals sine of theta, the middle is on the x-axis, the maximum is at 1, and the minimum is at -1. And I can mark off some numbers here if you like. We don't have a grid to work with, but I can say that this is 1, 2, 3. This is 0, obviously, the x-axis. This is -1, -2, -3. Forget about what B and C do. The fact of the matter is, if A is 3, it stretches this thing vertically by a factor of 3, which automatically, and I'm going to have to really adjust this to show you. I'm going to change this, everybody, just for the purposes of my explanation, to -1, okay? Let's imagine it's -1. So this A value of 3 vertically stretches things by a factor of 3, which changes the maximum and minimum values of the function to 3 and -3. It stretches it vertically by 3. The amplitude is 3. And then I know that the half does something horizontally to the graph. But I don't care about that because at some point everything is shifted down 1. And if everything is shifted down 1, what that means is that the lowest point is now going to be at -4. And the highest point is going to be at 2. And the middle of the graph is going to be at -1. So what is the maximum value of the graph? The maximum value of the graph, or the maximum value of the function, is 2. But 2 is the value of d plus the amplitude. I mean, d is this number right here of -1. So if you want to figure out what value the biggest value of y is, then take the middle of the graph and add the amplitude. So if you take -1 plus 3, you'll get 2. If you take -1 minus 3, you get -2. And this is my point here with this statement that I'm going to highlight in green. My point is that you can find the minimum or maximum, and therefore the range, without even worrying about graphing the thing. I mean, you have to kind of visualize what's going on. Anyway, the midline, what I call the midline or the medium value, is d. And then if you add the amplitude to d, you get the max. If you subtract the amplitude from d, you get the min. And again, the phase shift is c, and the vertical displacement is d. So please take a look at your work on page 250. There was a whole slew of questions that we were practicing with. Does anybody have any questions you would like me to go over? Go ahead, Julie. 16a. So we want to determine an equation of this graph. When I say A and D are the easiest things to find, I don't mean they're easy to find necessarily. It requires some thought. But A and D are typically the easier of the 4 parameters to identify. And I would recommend you actually having a ruler when you do this on an exam. If I were to draw a horizontal line across the top of this curve and across the bottom of the curve, that's going to tell me where the maximum and minimum are. And I know something we haven't talked about before, but this distance, we haven't talked specifically about this, but I think it's fairly obvious. That distance is 2 amplitudes. So if I can figure out the distance from -1 up to 3, which is 4, And I should know how to do it without counting squares, by the way. I can take 3 minus -1. So what I'm telling you is that this is a true statement, regardless of the sine or cosine function. Take the maximum y minus the minimum y, you'll get 2 times the amplitude. Well, that's 4. I don't want to write 3 minus -1. I could, but we know it's 4. And that means that the amplitude is 2. I'm showing you a very algebraic way of determining the amplitude. I think many of you would just look at this and say the amplitude is 2. Am I right there? Okay. The other thing that we can do, so what that means is I'm very tentatively going to say that lowercase a is 2. I may decide to make it -2, or I may not, but it has to have an absolute value of 2. The midline is halfway between that. And we can see visually where the midline is, but I suppose you could say that the midline, reasoning this out, would be the maximum minus the amplitude, right? If you go from the maximum to the midline, you have to take away the amplitude. So again, I'm choosing to show a very algebraic way of doing this. We're getting d is equal to 1. But again, I don't really know with this example that we needed to do that, because hopefully you can see that the middle of the graph is at 1. Yes? Okay. So now we can work on finding b. Now b is a little more work, but it's pretty straightforward how you find b. b is related to the period. So let me just, all over the place here. I haven't organized my work here very well, but we've determined d, we've determined a. What I would like to do now is determine b, but b is 2 pi over the period. So now we have to look at the graph and determine what the period of this graph is. And the period is how far it goes horizontally to do one cycle, and one cycle contains 4 of those pieces. So I wouldn't recommend starting someplace that's awkward to see. I would probably start here. There's a nice point because I can see up, down, down, up. I can see that it's pi. Is that okay, Julie? Okay, so the period is pi, which means that b is 2 pi over the period, which is pi. B is equal to 2. Let me write that over here. Now, just like I tentatively said that A was 2, I believe, I'm going to tentatively say B is 2 as well, although I could, just to be interesting, I could make it -2. I could make either of those -2. But I would rather not unless I had to. Okay, so now what do? Well, now what we do is we determine the value of C by sketching what a cosine function would look like with these 3 highlighted parameters. Okay. So I'm going to sketch the cosine function. What I'm really sketching here, I don't think we need this. What I am really going to sketch in order to identify what C is y equals 2 cosine 2 theta. Is it theta or x? It's x in this case. 2x plus 1. This is what I'm going to sketch. What I'm saying, everybody, is maybe C is 0. Maybe there is no C. Let's find out. So if I were to sketch this, the fact that this is 2 and this is 1 tell me that these are my boundary lines vertically, right? And the fact that this is a 2 in front of the x simply tells me it's going to repeat every pi. This is not helpful for me in determining C. I'm going to look only at A and D. Where does cosine start? I want everybody to think about that. Where does cosine start? And you don't want to say at 1, because that's only a very specific cosine function. Who can tell me where cosine always starts if A is positive? Sienna? At the top, at the maximum value, on the y-axis, right? So cos starts at the top. If it were sine, sine starts in the middle. And that means that cosine would start here. And since cosine starts at the top, it has no place to go but down. So if this were the function and c were 0, then this would be what the graph would look like. Are you with me? Except that's not what the graph looks like. The graph looks like what's in blue on the screen. And that means in order to turn this yellow graph into the blue graph, I need to take this thing and shift it to here. And then it sits on top of that other function. So how much did I have to shift it? Well, first of all, I had to shift it to the right, so I'm going to use a positive phase shift. And I shifted it 1 square. Now we have to figure out what 1 square is in terms of the grid. This is marked as being pi over 2. This is 0. So this 1 square would be half of pi over 2. Half of pi over 2 is pi over 4. So now we have the answer, an answer to the question. Okay, an answer. We have y equals 2 cosine 2 bracket again x minus c, which is pi over 4. Close all the brackets on that argument, and plus 1. Finding c is the most challenging part. And at some point, you're going to get an assignment related to this unit, and it's all about graphing. And trying to explain this on a written response, I haven't done it justice, even though I've used colors. What I would say is, when I take a key point, like this key point, what do I have to do to it in order to turn it into the point that actually is on the graph? And you would have to explain that by mapping or something. Is that okay, though, Julie? Okay. Any other questions from this assignment? All right. I would like to just, we have lots of time, right? We have today, we have tomorrow. We also have part of Thursday. Because you're not writing the multiple choice numerical response now until Friday. So I don't want to spend too much time doing this, but I think there's value in doing it. You're welcome. So what I'm handing out to you is a photocopy of basically all of those pages that I put on the monitor on the side when I'm explaining things in class. So at the end of the unit, I kind of compile them all together. You're welcome. For those of you that are in Physics 30 this morning, this one is very thin. Not because there's less material necessarily, although that is true. It's because a lot of the material here is something that you learn about and then you bounce off of in all kinds of different directions. Okay? So it may seem like it's thin, but there's a lot of material. I think it could be that your first couple of slides on this handout are in the opposite order to what I have up here. I'm going to talk about the common angles first. Frankly, I would expect everybody at this stage of the game to know these common angles in terms of degrees to radians. It should almost be just second nature without even thinking, or with little thinking, that pi over 4 is 45 degrees, pi over 3 is 60 degrees, pi over 6 is 30 degrees. Sometimes you have to think, though, just to make sure that your brain, which can be on autopilot, isn't giving you the wrong information. So it's expected that you're able to recognize these. It makes your job a lot easier in this unit and also in the next unit. As well, you have to be able to convert from one type of angular measure, say radians, to another, say degrees, or the other way around. And that includes exact values, that includes decimal values. That's an expectation in this course. Arc length, I know that it's very likely a couple of you will forget this, so I will try to highlight it. Physically and verbally. Theta must be in radians. It has to be in radians. I don't know how you're going to remember that. Quite often, if your calculator is in degree mode, I shouldn't say quite often, if your calculator is in the wrong mode, you might get an answer that just totally doesn't make sense. Actually, it's probably most of the time. So it's the old adage that your math teachers have been telling you for years. Look at your answer and ask yourself if it's reasonable. I mean, a very quick illustration here is if I told you we had a radius of 4 centimeters and the angular measure was 120 degrees, what's the arc length subtended by that? If you just took the radius, which is 4 times 120, you're going to get 480 centimeters. That doesn't even make sense. The radius of the circle is only 4 centimeters. How can the arc length be 400 centimeters? So that might be a clue to you that when you calculate an arc length or you calculate a radius or you calculate an angle, that you've done something wrong. Okay, so you have to be working in radians for that formula to work. Review from Math 20. You do need to know basically that positive rotation angles are counterclockwise on the coordinate grid from the positive x-axis, whereas negative rotation angles are clockwise. The reason for that is a positive rotation angle sweeps through the 4 quadrants in the order that they're numbered. 1, then 2, then 3, then 4. Also review from Math 20 is the concept of a reference angle, which we use later on in this unit to calculate rotation angles when we're solving an equation. So the reference angle is always the shortest or smallest angle, and we don't care about direction. There's no positive, negative. It's just the number of degrees or radians. It's the smallest angle between the terminal arm and the x-axis. And if the smallest angle is found by taking that location of the terminal arm and going towards the x-axis by rotating down, then so be it. If the smallest angle is found by taking the terminal arm like it is here and rotating it up to get to the x-axis, so be it. It's the smallest angle. But again, notice that we don't put arcs. We don't put arrows on the end, arrowheads on the end of the arc for a reference angle. If we did, that would probably imply that there's a direction to it. There isn't. Rotation angle, however, is from the positive x-axis. If you're talking about a positive rotation axis, is from the positive x-axis counterclockwise until you hit that arm. What's not in here, it just occurred to me, I don't have a special view here or page to talk about coterminal angles, I don't think. You should know that a coterminal angle is just another angle that ends in the same place. The unit circle, some kind of chippy ideas that you need to know about the unit circle is what it is. It's a circle with a radius of 1 centered at the origin. You also need to know that the equation of the unit circle is x squared plus y squared is equal to 1. And probably more significant than all of this other stuff, although it's important as well, is knowing that the x-coordinate on the unit circle is the cosine of the rotation angle, and the y-coordinate on the unit circle is the sine of the rotation angle. And let me spend some extra time here talking about this. So when I say you need to know the coordinates of the points on the unit circle whose rotation angles are multiples of these common angles, you know what I'm really telling you you need to be able to tell me the sine, cosine, tangent, secant, cosecant, cotangent of any of those special angles on the unit circle. Because if I'm telling you you need to know the coordinates of these points, and I'm telling you that the x-coordinate is cosine, then you need to know the cosine. So if I say to you, what is the cosine of 11 pi over 6, the answer is root 3 over 2, because when you get around to 11 pi over 6, which is right here, kind of in the center of your screen, you can see that the x-coordinate is root 3 over 2. But going back to this point at the bottom of your screen, sometimes I give a question which I believe is easy and it stumps people. And it's a question like, a rotation angle has a value of 428 degrees. I better go 408 degrees. It intersects the unit circle at 0 point A, B, comma, 0 point C, D, with both of those coordinates rounded to the nearest hundredth. What are the values of A, B, C, and D? And I mean, it stumps some people. But if it intersects the unit circle, then the x-coordinate is the cosine of 408 degrees. That's all you have to do is go cos 408 in degree mode. It's actually a diploma exam kind of question. So the x-coordinate of the point of intersection of that rotation, that terminal arm for that rotation angle with the unit circle is 0.67, and the y-coordinate is 0.74. So the answer would be 6774. It's, I mean, it's a question that I think is kind of a basic question. You need to know cosine gives you x, sine gives you y. But when you see it, you may forget about that detail. In addition to knowing the coordinates, because you're expected to know the exact values of trigonometric ratios, for those of us that solve equations with the unit circle, we know that it makes our lives easier. We can do in 1/5 the time, or maybe even 1/10 the time, what it would take somebody who's not familiar with the unit circle to do when solving an equation. If sine of theta is 1/2, it's pi over 6 and 5 pi over 6. If you really know your unit circle, sine is the y-coordinate. If you don't, then you have to find a reference angle, and that's okay. I'm just saying it's going to take you longer. And then identify the two quadrants that the angle is in. I've just put on here all 4 of the quadrants. Remember, I think it's a waste of your time, exam time. I've seen students do this for the exam to start, and then all of a sudden, I'm seeing people spending 15 minutes constructing this beautiful unit circle to use for their exam. Just construct the part of it that you need. Ryan. You only have quadrant 1 and 2. So you're missing a whole bunch of stuff. Okay, I will, before the end of the class, I will get the rest to you. So when I go to here, you don't have this. Interesting, okay. Appears to have been a glitch in my photocopying skills. So I'm going to go through this, and then I will send it to the photocopier again with the right number of pages, and I will get it to you. So you don't need to write any of this down. That's going to be given to you in about 10, 15 minutes. Last year in Math 20, thank you for that, Ryan. Last year in Math 20, you were taught about the definitions of sine of theta, cosine of theta, and tangent of theta for rotation angles on the coordinate grid. And obviously, as theta sweeps through different quadrants, x and y can take on different characteristics. They can be positive or negative. And that means sine and cosine and tangent can be positive or negative. And you're expected to know where they're positive and where they're negative. But this year, we've introduced these other three trigonometric ratios where cosecant is the reciprocal of sine. I'll show them to you this way first. Cosecant and sine are reciprocals of each other. Secant and cosine are reciprocals of each other. And cotangent and tangent are reciprocals of each other. So what this means is that if sine is y over r, sine of a rotation angle is y over r, and cosecant is the reciprocal of sine, then cosecant of theta is r over y. It's flipped over. Secant of theta is the reciprocal of cosine, so it's r over x. Cotangent is the reciprocal of tan, and since tan is y over x, cotangent theta is x over y. All of these questions you did in Math 20, where maybe you're given one of these trigonometric ratios and asked to find the other two, now become questions where you're given a trigonometric ratio and you're asked to find the other five. So anything that you were expected to do in Math 20, we just layered another set of trigonometric ratios on top of it. In your notes, I actually rewrote all of these trigonometric ratios, and I said, if it's on the unit circle, sine is y and cosine is x, and I changed all the r's to 1. I decided not to do that in this review handout. I'm just reminding you that if it's on the unit circle, use r as 1. This, to me, I put this up here and in your review handout because I want to be accessible to you if you need to refer to it. But this, to me, is just very cluttered and confusing to look at. Not for everybody. If you want to know where sine is negative, think of the definition of sine, which is sine is related to y. It's y over r. So where is sine negative? Wherever y is negative. And that's why I have sine of theta is negative and sine of theta is negative here and here. It's because y is negative. So I guess what I'm telling you is don't set out to memorize this. Please don't try to memorize this. Try to understand it. One of the biggest mistakes that can be made here is if you're trying to find a trigonometric ratio, you don't take into account the proper quadrant. So for example, if I tell you in a problem that tangent of a rotation angle is 12/5, and someplace else buried in amongst all of the information I say the rotation angle terminates in quadrant 3, what's the value of sine of theta? Well, you need to know in quadrant 3, x and y are both negative, even though you're not seeing it there. Which, by the way, for a multiple choice question makes it easier for you. Because if I said that tan is 12/5 and the terminal arm lies in quadrant 3, and it's a multiple choice question that says what is sine of theta, probably 2 of the choices will be positive and 2 will be negative. But you know if it's in quadrant 3, sine is negative. To solve a linear trigonometric equation, what do I mean by a linear trigonometric equation? A linear trigonometric equation would be something like 6 secant theta minus 3 equals 0. Nope. 6 secant theta minus 12 equals 0. That's linear, because the trigonometric ratio is raised to a degree of 1, which is linear. It's not raised to a degree of 2, which is quadratic. What you would do is you would rearrange this for the trigonometric ratio. We would get 2 because you add 12 to both sides, then you divide by 6. You would go a step further and then write cosine of theta equals the reciprocal of it, and then you would solve the equation. And if you know the unit circle, it's at the 60-degree mark and the 300-degree mark. If you don't, then what you have to do is this third point. Find the reference angle, identify the two quadrants, do the sketch, determine the rotation angles. So you would sketch a terminal arm in quadrant 1 with a reference angle of 60 degrees, which would be what you would get if you went inverse cos of 1/2. I think. Can you check it out, please? You get 60 degrees, and you would say since cosine's positive, it's in quadrant 1 and quadrant 4. I'm not going to draw this, but if you sketch a reference angle of 60 degrees in quadrant 1, the rotation angle is 60 degrees. If you sketch a reference angle of 60 degrees in quadrant 4, the rotation angle is 360 minus 60, which is 300 degrees, and you could also work in radians. If it's a quadratic trigonometric equation, you simply factor it so that you get two linear trigonometric equations. That leads us to the last couple of days. You have to know the features of sine and cosine functions. And I would go so far as to say, I mean, you need to know sine has a max of 1 and a min of 1. But you need to know the sine starts at the origin or starts in the middle on the way up and repeats in one period. Cosine starts at the top on the way down and repeats in one period. And then you need to be able to identify features of graphs, potentially on a written response sketch a graph. I'm not going to tell you what the written response will be, but I have seen those written responses before, where you are given the equation of a trigonometric function, asked to identify the values of A, B, C, and D, asked to explain what the amplitude and the period and the vertical displacement and the phase shift are, and then asked to graph it. 5 marks. It's a reasonable thing to expect you to do. So that's it. I'm going to now hand out a collection of multiple choice numerical response questions for you to practice on that we were working on today and also tomorrow. And then I'm going to, I don't think I'll print the whole thing. I'll just print you the second half of that handout and get it in your hands here in about 10-15 minutes, hopefully. I'm not sure if I've mentioned this before, but I think I have. Maybe not in this class, but in your Math 20 class, so I'll mention it to everybody. You know, your textbook is a great resource for problems that could potentially be turned into multiple choice numerical response questions. Particularly those questions that are the final questions in all of your practice sets. So, for example, number 16 at the very end, or sometimes there's a word problem at the very end that can be quite complicated. Maybe it has to be solved using a system of linear equations or some other application from earlier grades. And the fact of the matter is, sometimes what we do as teachers is we look at those problems and we go, can I make that into a multiple choice question? Can I make it into a numerical response question? If the answer is yes, well, I wouldn't be interested in doing it unless I could do it, so I do it. Please get started on it. Please be patient while I take attendance and send the rest of those pieces down to the photocopier, and then I'll come around and I'll give you a hand.